So this is what we're going to cover in the tutorial. Well, by the way, before we start, how many of you actually have done time series analysis before? Half? Using AutoRegressive Integrated Moving Average model, how about? 2. Okay. So maybe at the end, I will have to ask you to share with me what kind of time series technique that you actually use to study time series analysis. What we are going to cover today is primarily the class of autoregressive integrated moving average model with and without seasonal components. So the short name is SARIMAX. The X at the end is really the explanatory variable. The way we are going to do the tutorial is that there are 5 different sections. I probably will spend the next 15-20 minutes to talk about some introductions, do some simulations, and also have you guys work on a demo as well, if you can clone the repo. And then we'll dive straight into this class of time series model. Now, it's actually very important that we understand the mathematical formulation as well as the underlying statistical assumptions of many of these models. And so we'll spend a little bit of time at least set up the right framework and introduce the notation for us to do it empirically. So we'll spend a little bit of time on doing that in section number 2. And along the way, you actually will find out that we will spend a lot of time visualizing time series, doing exploratory data analysis before you even jump into the modeling. And then sections 3 and 4 are the modeling without the seasonal component first, and then with the seasonal component. And then we have some closing remarks. Now, as you can see, we actually include more notebooks than I think we can cover in a 2-hour tutorial. So, and I can go as fast and as slow as the class progress. So the notebook is written in such a way that it's fairly self-explanatory. And so after the tutorial, if we cannot cover everything, I want to make sure that I touch on the important points so that you can go home and continue to use the notebook and study it. And in fact, at the very end, we include some references for you to do a more deep dive into some of this model as well. I really I have several colleagues here with me. We have Jonathan and Whitmore and Matt Mollison. Matt actually create, I would say, 90% of the code here that I'm going to share with you. So both of them will be helping out in the tutorial to make sure that you can run the notebooks. Okay. I also have a colleague also sitting here, one of our senior data scientists, to observe this tutorial, make sure that I did everything correct. So let me get started if you don't have any questions. First of all, I want to make sure that you actually load this notebook, because as I walk through it, I would like you to run the notebook as well. Can I start? Okay. So, sure, Jonathan.
If you go to the readme part.
What happened?
I just want to mention that they should do this.
Oh, okay, sure.
That's kind of a weird thing that they might not have done.
Okay. Where is it?
Yeah, just hit reload fresh on this. So just one modification to your standard Anaconda install is this pip install ---- pre stats models ---- upgrade. This will give you the release candidate for stats models, which they'll end up doing next week probably.
Yeah.
And this just allows you to do things starting from notebook 3 onward. But it's easier if you just set it up now and start running notebooks from that. So that's just the thing. If you haven't done that yet, it's a good time to just try it.
Okay.
Where was that link? I'm sorry. Or where?
So if you go to this bit.ly link,
Right here.
svds-pydata.ts, that goes to this kind of longer link, and then that's in the readme.
Yeah.
Raise your hand if you need some help. And
Yeah, they'll come around to help you. And throughout this tutorial, I actually will be using Python. I will not be using R. But later on, after this tutorial, I'll post some of the notebooks on R. At Berkeley, I actually use R to teach the class. Okay, so let's dive right into it. So some of the common use cases. So why do we study time series? Well, some of you probably know, right? It has a lot of common use cases. Everything from government forecast their budget, government forecast their expenses, especially key economic indicators that are published on a monthly basis on some of the government websites as well. Right now, I think just past Q2, close to Q3. So actually, back several weeks ago, you hear a lot of the earning releases from company as well. So they need to forecast their sales and their revenue and earnings also. CMS here is the medical society that need to project the medical expenditure for the nation as well. And the one below that is the National Center of Education Statistics, that they also on a yearly, actually on a quarterly basis, need to forecast the budget as well as number of teachers, number of students in the coming year for them to allocate resources. And I include a few more as well. So when we are looking at the time series, we actually have to look for some common characteristics because that has a lot of implications when it comes to modeling. So I include a few examples here. So, and by the way, you should run it. I already ran the whole notebook, so I'll just scroll down. But as you go through it, you should run some of the cells, right? So the first one I include here, this is actually a very popular data set. It's actually included in several textbooks, as well as the Sarimax Stat Models website as well. It's the International Airline Passenger Traveling data set. And one of the reasons that this data set is so popular is that it actually captures several characteristics in many, many different time series. So one is, as you can see, there is an increasing trend over time. And what we call the volatility, the fluctuations around the trend is also increasing over time as well. And so these are two very, very common characteristics in many of the time series that you see. Another one is the annual sales of this. So if you, for example, take away the fluctuations around the trend, all you will have left is obviously just the trend, right? And in fact, for those of you who have done time series analysis before, you may actually have to first estimate the trend and then take out the trend before you do any of the analysis. And this is one of those that you actually see that there is close to a linear trend in this particular time series. So these fluctuations here on a series that, because this is an airline, passenger traveling series, as you can imagine, there is something called seasonality. So at certain time of a year, the fluctuations may go up, and certain time of the year, the fluctuations may go down. Yes? Closer? Okay. I'm almost kissing the thing. Okay. Okay. So what was I trying to say? So I was trying to say the seasonality. And so one of the very good way to visualize seasonality is a box plot. So as you can see, this is a monthly series that span over well over 10 years. If you only plot the distributions of this series just over the month, which you see something here. So you can see that there is a very prevalent spike in terms of this series around the summertime, as you can expect. Now keep this in mind, because later on when we explore the time series, these are some of the techniques that you'll be using. You'll be plotting the time series plot, and you may be plotting some of the box plot as well. So the second one, this is the Earth surface temperature. This is another very famous series that actually has been used in many of the textbooks also. And it highlights two things. One is the fluctuations again. But more importantly is that this series actually seems like changed the structure over time. Between 1880 to roughly around 1960, is the average temperature is actually stay fairly constant, even though it go up and down from year to year, but it stay fairly constant. Over time, though, since 1960, it actually has an increasing trend. Now, my series only go up to around 2010. If you continue to plot the series, actually continue to go up. And so trying to notify the change in the structure of a time series is actually very important, because every time when you apply a model and your model is going to rely on the historical information for you to do the forecast into the future, and if the historical information is not applicable to what you think will happen in the future, then no matter how good your model is, it may capture the past but may not capture the future. So keep this in mind. So that's why whenever you do a time series analysis, just plotting the series to begin with is very important. And this one highlights the change in the structure of a time series. Third one is still variations, but it's variation around a stable mean, which is what you see here. This is the return series of the Dow Jones Industrial Averages return for the last 10 years. As you can see, the average stay around zero. The return stay around zero, but then it fluctuates a lot over time. And in particular, there are times where the fluctuation is very strong. This particular pattern is extremely common in a financial time series. I actually spent, before I joined Silicon Valley Data Science, I actually spent the last 10 years working in the finance industry. And so this is one of the series that I did a lot of modeling on. The last thing is cycles. So, right here, sorry, I may not. Give me 1 second. Okay, so another thing is the cycle of a time series. Here I actually plot several things as well. Seasonality is a repeating cycle that happen on a regular time frame. But as you can imagine, that there are repetitions that are not necessarily on, let's say, every year or every quarter. Business cycle is actually one of the most famous one. So as you can see that this is the sunspot that is spotted on the sun in the, in the last 200 years or so. Another thing I want to point out is that in many of the data analysis, you may just plot the histogram or a density functions of the underlying series. Whenever you look at a time series, it's actually very important that you plot the time series plot in order to see the dependency over time. If you plot only a histogram, you will not be able to, the time element is taken away. So you only see the distribution over all of these years. You see here, but you will not see where the spike up is coming from. And so in time series, you need to pay attention to that, because the dependency, meaning what happened in the very recent future, may matter in terms of your modeling. These two I actually will cover later, so I'm going to skip for now the autocorrelation and partial autocorrelation functions. So what's next is the demo. I would like you to run the next servo cell in order to get into the widget. I've already run it, so you have to run it in order to get to this particular cell. So let me know once you're done, or I will ask you in a minute. Seems like you guys all ran it. So, so what this does is that it create a widget for running a bunch of simulations and estimate the simulated time series. So let's do some simulation first. Now, in fact, these are some of the models that we are going to study later today. And it's actually very beneficial to try to simulate a series from an underlying process. When I say process, I actually mean stochastic process. Because if you know exactly what the model is, and if you know what the patterns that is generated from that model, when you actually apply to a real-world data set, which you don't know how it is generated, it's actually would be beneficial for you to identify what would be the candidate models to use. So here in this widget, as you know, we are studying autoregressive integrated moving average model today. So we are going to simulate a few autoregressive moving average model for different orders. So as an example, so if you choose, let's say, AR stands for autoregressive. If you choose AR order 1, and if the parameters of that model is 0.7, I know that now it seems a little bit hand-wavy. Later on, we actually will get into the equations. And when we do that, that's what the graph is going to look like. So let me not do any estimation yet. So when I do that, this is what you will see. You just simulate a time series from an AR1 model. Now I can do another one. I can simulate a time series using an autoregressive moving average model of order 1 and 1. And let me say the parameter is -0.3. So that's another series too that we just simulate. The reason that you see what we call in-sample and out-of-sample just from the simulation point of view may not make sense because it's actually just one series. But later on, we are going to estimate a model, so we want to leave out at least some part of the series for us to test our model on. And so that's why you see the in-sample and out-of-sample data. So let's say after we simulate this model, simulate a series, and later on we want to estimate a model, and we use, let's say, AR2, so P equal to order 2. And after we estimate a model, you can actually plot and see how the model fit this particular series as well as the forecast. Now again, right now it may not make a lot of sense to you because we're actually going to go over that in the next 3 sections. But I just want you to get a feel of, play around this demo a little bit. Get a feel of what different series look like coming from different of the autoregressive moving average models. And in fact, after you do the estimation, there is a result here and the residual of your estimation. So this is what I want you to do in the next 5 minutes. So write down, or at least talk to your neighbor, a couple of examples of time series that you have encountered in your real life. I'm sure most of you encounter some time series. Like if you wear Fitbit, you already collect some of the time series on yourself, right? And use this tool that we have developed to simulate a number of series. And get a feel of what different series that you look like. And more importantly, whether or not you can actually simulate some series that you think you can encounter in real life. Okay, so play around with this tool. Spend the next 5 minutes or so. And my colleagues will be, well, where are they? They will be walking around and see if you have any questions.
Can you scroll to show us which widget settings created those?
Yeah.
Thank you.
So this one that I use is AR1. And it's ARIMA 101. So you see that the AR order is 1 right here. The parameter is 0.7. I set to 0.7. And then for the moving average order, it's also 1. And I set it to -0.3. So you should slide the ball around and play around a little bit. With this tool, it's very useful. Without that, you actually have to write code to simulate it. You can see how much code the amount of codes that we use to create this. So for some of the graph, by the way, so for some of the graph, when you do the simulations, you have to adjust the limit on the y-axis. So for example, this one that I just simulate, it goes all the way below the x-axis, right? So you have to change the y limit a little bit. So let me make it smaller. So that you can show the whole graph. Have you guys been able to simulate anything that you have encountered or you have seen in real life?
Put a upward trend in the data, or can you do that?
Put
Put an upward trend in the data?
a
Or maybe you can do that, what do you say?
with this series or in the data in general?
Or I was just wondering in this series, because I don't understand exactly all of the toggles. I imagine that in order for the lag 2 to happen, you should set order to at least 2.
Oh yeah, that's for sure. Yeah. So this widget only allows you to simulate up to order 4. You see that? But for you to do order 4, you have to set it to 4, right? Mm-hmm.
Can I ask you a question?
Yes, of course, please. If you have any questions, by the way, just feel free to ask me.
So in the very beginning, you had flights over time, airline flights over time, and you kind of eliminated the seasonality. How did you do that?
How do I reduce the seasonality?
Yeah, because it was like this, and then started going up.
Oh, yeah.
Pretty flat.
Yeah, so let me go up. These are good questions. This graph right here. Yeah. So the question was, I have this graph right here that has a time series that has seasonality and a very strong upward trend. What exactly did we do in order to have the plot below? So for any graph, for any time series, we can actually estimate the trend and we plot only the trend. So that's what we did. We only plot the trend and not the. In this case, for example, you can estimate using a linear trend. So it's like a line, A plus B, as a function of t. So as the time index go up, it will go up by the increment of the slope that you put into the line as well. Yeah.
So if you have a window of like 10 years, you just fit a straight line through the data points?
Yeah, you can.
Okay.
Yeah. So it's fitting a linear trend literally. There are trends that may be growing going exponentially, then you have to fit a quadratic trend. Mm-hmm. So again, this you only plot the trend. Okay. Are you still working on it? Is there anyone still working on it? If not, I'm going to move to the next section. No responses. So how about we move to section 2, all right? We can come back to it because a lot of this this is just give you a flavor of what we are going to study today. The important thing is we actually study it. So if you can open up the second notebook. So notebook section 2 on exploratory data analysis and the class of ARIMA model. Now the one that you have, I only include some of the takeaways, at least for this tutorial. Later on, I'll give you the one that I am going to show you right now. Now, so in order really to study the class of autoregressive integrated moving average model, we actually need some terminology. We need to understand what is a stochastic process. We need to understand when we are talking about time series exactly what we are talking about. We also need to understand some notion of stationarity and octocorrelation and things like that. So for the next 5 minutes, it's maybe a little bit math heavy. So before we dive in, I just want you to get a few takeaways from the next 5 minutes or so. So number one is that the observed time series is actually treated as a realization of some underlying probability model. At the end of the day, this model has a very strong background in probability framework. So whenever we see a series that you see from the data, we are treating them as a realization from the underlying stochastic processes. And we're going to study a certain class of probability model. Okay. Wow, you are sitting in the middle and then even you can't hear it. So meaning half of the people can hear me. Okay. Study certain class. Okay, so we are going to study a class of model that is very appealing and is very simple in terms of the structure. And in fact, this is why when we first study time series, this is almost one of the first class of models that you should study, because with the foundation in this model, you actually can study many other models as well. We'll also, so another takeaway is that the concept of weak stationarity. This is very important that the underlying time series that you are studying satisfy this condition before you apply it to the model. And we'll talk about what weak stationarity means. And the concept of octocorrelation functions and partial octocorrelation functions. These are the main tools that we'll use to study the dependency of a time series. Okay. So I think many of you should be familiar with the concept of covariance. In the case of time series, we talk about octocovariance, meaning the covariance of the series with itself, okay, with its past. And a corresponding concept to that is the correlation, octocorrelation. So the correlation between the series and itself. Now, for the correlation to make sense, we actually need the underlying mean of the series and the variance of the series to not change over time. So remember, you have a time series that is changing over time. If every time period your mean is changing, you actually do not have enough information to really understand the mean and the variance of the underlying series. And so this comes the concept of stationarity, meaning you want the series to be, I'm a little bit hand waving here. You want the series to be stationary in the sense that the underlying mean and the underlying variance don't change. Okay, so just keep that in mind for this tutorial. I will put in, so this notebook, you don't have it yet. So I'll put in on a GitHub some of the math notation behind this stuff. And I'll also have some references to really define a stochastic process, a time series, and the notion of dependency. As you can see, it's a little bit involved, but it's actually really necessary because otherwise you estimate a model, it gives you error messages, and you don't even understand why it gives you error messages. It's exactly because some of the underlying assumptions don't even satisfy. Okay, so let me go back. Okay, so let's start exploring some of the time series. Again, follow along, run your cell. This is the setup. So the data. Oh, by the way, let me mention this. Right here, I comment out some of the comment. So there are a lot of time series data available on the internet. And if you use the remote data access from Python, you actually can download a lot of those time series. And so here, I actually download just three examples. One from Yahoo, the Citigroup stock price, and I call it C, which is the ticker symbol. Another one is U of Michigan consumer sentiment, which I download directly from Fred. Fred is Federal Reserve St. Louis, and they offer, I think, close to 400 time series available right now, and it's updated on a monthly basis for most of them. So it's called Sentiment. And the third one is, this one you actually can download either from Fred or Yahoo. I download it from Yahoo. It's the 10-year Treasury rate. It's the interest rate associated with a 10-year bond. Because I'm afraid you may not be able to do it because of the internet access. I already downloaded it, and I save it in the data set, and you can just read it in, which is right here. So read in the data. And first thing you do, of course, is to look at the structure of the data. And pretty soon you'll find out why okay, it sounds very simple, but why do I want to do that? And here's the reason. So if you look at the one from 10-year Treasury, I thought that I download just one series, when in fact you actually have opening price, the highest of the price on that particular day, low, close, volume, and adjusted close. So you actually have 6 series associated with one series that you thought you would just download. So it's always good to take a look at the structure of your data before you go further. Same thing for the Citigroup series. And so here I just plot the first 10 observations associated with the closing price. And also good to know that what time period are you talking about? Have you really downloaded the time period that you want from the database? For the remaining sections, I will focus on the sentiment time series. So we are talking about exploratory time series data analysis. So exactly what are we exploring? So we are trying to exploring some of the patterns that we talked about before. And here in particular, we are trying to explore the dependency structure of the series. Okay, and this is what we'll be looking at. So first, we'll be looking at just the pattern of the series. Now, as you can see, this series, again, this is consumer sentiment. It drastically came down right before 2008, and it stayed down for a good several years, and then it slowly start to ramp back up. Now, if you are going to build a model later on, include the whole series, well, then you really have to think about, okay, well, this drastic decrease in your time series, whether or not you really want to train your model with that included if you want to do some forecasting later on, because this may not represent what is going to happen what's going to happen in the future. Okay, so that's why it's good to at least just plot it out to see what's going on. Second is that to look at the dependency of the time series, which we introduced the concept of octocorrelation before, this is a graph of the octocorrelation functions. Octocorrelation functions is a function of the time displacement, meaning how far apart the time series itself and its path is. So the first bar, okay, this is 0. 0 obviously is 1, right? The series with itself is always perfectly correlated. But the series with its first pass is represented by this in terms of the octocorrelation. The second one is the octocorrelation between the series itself and the second pass, and so on and so forth. Here I only plot up to 20 lags, which is controlled by here. You can plot more, you can plot less, depending on how long your series is. We actually not that long ago did a project. In that series, we only have 30, 40 observations. So plotting 20 lags may not make a lot of sense, right? So depending on how long your series is. Now, I have a very long series here. So 20 lags seems okay. You have a questions?
What is the y-axis?
The y-axis is the value of the correlation. So it's supposed to be bounded by -1 and 1. So it's a good question. So at 0, correlation is supposed to be 1 because the series itself is perfectly correlated with itself. Here means the value looks roughly like 0.9. So which means that the correlation of the series and its first lag is 0.9. It's very, very highly correlated. Now, the pattern of this correlation is something that we have to pay attention to because it sort of gives you an indication of how far back the series will give you information for the current value, right? We want to know about this because, again, in at least for this class of model, we want to understand how much information in the past can help us to predict the future using the same series, okay? Now, so octocorrelation. Partial octocorrelation, yes?
One quick question. What does the banding mean?
Yeah. So the band is by the way, so this is the sample octocorrelation. And by sample, we really means that it's an estimate of the correlation. And so any estimate, you have the standard error coming with the estimate. So the band is the 95% confidence interval associated with the octocorrelation.
By band, you mean blue?
The blue cone envelope. Yes, thank you. So the partial octocorrelation is similar to the correlation, but you should interpret that as condition on other correlation, what this correlation is telling me. So it's very similar to in your multiple linear regressions, condition on x1, what is the beta 2 telling you of associated with x2, right? This is what partial means. Another way, so again, these two graphs are the main tools that we will be using to look at the dependency structure of a time series. Now, there is an alternative way to do that. It's more intuitive. How come I hear car sounds? Okay. So another way to do that is actually plot a scalar plot, right? So you plot the series itself with its path, depending on how far past. So the first one here is lag number 1, the series itself, original series, right? And its first lag. And the second one is, again, if it's almost lined up like a strict line at a 45-degree line, you see that the correlation is very strong. And then this one is the series itself and lag number 2, lag number 3, etc., etc. So this scalar plot matrix is another way for you to visualize or communicate with your colleague or other people or clients about the strength of the correlations of the series with itself. This is very useful, right? The octocorrelation function is very useful, but may not be very intuitive to people who are new to time series. And so sometimes that's why this scalar plot matrix can communicate the idea. Okay? Yes?
Do you have a good
The covariance? Yeah. So yes, the correlation is just normalize the covariance by the standard deviations. Correlation is better because covariance will be affected by the underlying unit of measurements. And so in time series, it will, so for example, if before I showed you the airline series, the number is like in the millions, and so covariance will be affected by that. So the number could be very big, and so it may not necessarily give you an indication of how strong that numbers mean. And so once you normalize by the standard deviation, everything is bounded between 0 and 1, so you can say, oh wow, okay, 0.9 is a big number. Yeah, thanks. So in different notebooks, we include some of the code to plot all 4 graphs simultaneously. So for you to do the exploration much easier. And in fact, in some of the textbooks you see, these are the graphs that they normally will show you, right? You plot the time series itself. You also plot the distribution of the series, octocorrelation functions, and partial octocorrelation functions, all on one graph, all on one screen for you to explore. Okay. Okay, I'm going to spend the next few minutes to talk a little bit about the ARIMA model before we even estimate it. And another reasons I want to do it is that if you actually go to the stat models, which is what we're going to use, by the way, Python stat models, TSA, and in particular, we'll use the state space class models. You see a lot of notations there, and the notations there is very dense. And so at least I want to give you a couple of examples of how to unpack some of these notations. So forget about seasonality for the time being. Just focus on the autoregressive and moving average, integrated moving average model. There are 3 key things that you need to set when you try to estimate a model. Say that again. I can hear you. I really can't hear you. Can you say that again? Can you speak?
Which notebook?
Oh, notebook number 2, section 2. So you see right here, section 2, ARIMA models _ tutorial. Section 2.3 in particular. So if you go to the stat models website, and this is the equation you see. So first of all, autoregressive integrated moving average model are often expressed in what they call the backward shift operator, which is represented by B here. What it really means is that if you apply this operator, let's say B times xt, then automatically you get xt minus 1, right? So equation-wise, so let's just say, for example, this is the underlying model that we have in mind. Is the current value zt, which is a function of its past value zt minus 1, plus the random noise, and some function of the past random noise. Then you can actually rewrite this model using the backward shift operator. So which is what I'm going to do here in this very simple example. You move the zt to the left-hand side. So all of a sudden you create the differences, right? The first difference is the difference between the current value and its immediate past, which is ct minus zt minus 1, and which is equal to the shock plus its past value. Some parameter times its past value. And so I factor that out. That gives you the backward shift operator. This is back to the notation you see above. Another reason is that this notation, this backward shift operator, is used very, very often, is that in this kind of time series, to check the stationarity. Remember we talked about stationarity before? Many of those are checked using the characteristics of these backward shift polynomials. And so That's why they're expressed in this notation. I won't have enough time to go over all the math, but just want to give you a flavor of it. So this is another example. Then again, whenever you see a notation from backward shift operator, it's always a good idea to practice to reverse the operation and see what the underlying model is. Because at the end of the day, you have to interpret your model. It's better to know exactly what coefficients are we talking about. So that's another example. The integrated, in terms of the autoregressive integrated moving average model, integration here really means difference. Difference one time, difference two times of the series itself. So for example, here is integration of order 1. So integration is not the integral, but it's the difference in this setting. I didn't set the terminology, by the way. Someone else before me did. Okay. This basically is what we set up here is that the general procedure of building a non-seasonal autoregressive moving average model. We'll talk about how to do the seasonal one. So we'll try to examine the seasonality of the underlying process of the series. If the process or the time series that you look at, I should actually change that to time series, is not stationary, using this approach called Box-Jenkins approach, a very famous approach that made a Riemann model so popular in the last 40 years or so, is that you will have to difference enough times in order to make the series stationary. Once you do that, then you identify using the ACF and the PACF functions to identify the order of the autoregressive model. So again, you try to identify the integration order, the D. Is D equal to 0, D equal to 1, etc. And then you try to determine what P and Q would be. Now, in general, that's not the end, right? I sort of identified a model. Then really actually just give you some clues as to what the autoregressive moving average model as a starting point. In practice, you actually have to test a few different models. You have to do model diagnostic analysis. You have to re-specify the model if your diagnosis doesn't make sense. And you have to select among several models that may you may have to select among the models a model that among your candidate models, and more importantly, perform whatever inference or forecasting that you need. So I know there's a lot of notations to go over. Before we move on to really try to develop some of these models, I want you to do this exercise. You import this file. Oh, by the way, I actually show you some of. I shouldn't be showing that. So I want you to import a file and then follow the steps of exploring the time series, and it's recorded in your notebook. Give you a few minutes to do that before we move on to the next sections. It's very important that you do the exercise because I'm going to use the same series to build the autoregressive model later in section 3. If you have any questions, just ask. We have 2 people here to help out.
It's just about an hour.
Oh yeah.
So maybe when people are done with the exercise, it'd be a good time for a break.
Oh yeah. It's almost at the 1 hour mark. So when you're done with the exercise, maybe we can all come back at 4:10 or so. Yeah. Okay. So let's move on to section 3. So if you use, you guys have questions?
Do you want to take questions through Twitter and we can answer them after?
Oh yeah, absolutely. You can answer them after. Yes, absolutely. Yes.
So when is partial autocorrelation more useful than normal autocorrelation?
Can you repeat the question? So the partial autocorrelation, I hear that, but what's the questions around?
When is that more useful?
Oh, yes, I'm going to go for that. Yes. Which means the exercise is successful, that sparked your interest. What should I use with the ACF and PACF? Okay, so let's start with section 3. So use the section 3 notebook and import the series again. Again, follow along. Okay, first part is actually answering your questions. So model identification. So now that we have explored the time series, trying to look at the dependency structure and looking at the pattern of the series itself, how am I going to link this into building an autoregressive integrated moving average model? So I sort of summarize here the procedure. So again, one is trying to find out how many degree of differences that you may need. And that may depend on whether or not the underlying series is stationary. Second is that we are going to study the pattern of ACF and PACF. And so below, we actually summarize the table for different types of models, right? Now, again, this is assuming that we have already defined the series enough time so that ACF and PACF in a series that is stationary, so that ACF and PACF can be used to study the dependency structure of the time series. So if we have an autoregressive model, the structure of the ACF is supposed to look like is slowly tail off. Now, the graph that we have from the series is just coming down exponentially. But there are also series that actually, if it is negatively correlated in the past, it actually go down like this, right? Like a cone. So that also consider as tailing off for the ACF graph. But then for the PACF, it actually will cut off fairly drastically after a particular lag, say lag P. So that allows you to identify some starting point for your autoregressive models. Now, if it is a moving average, again, if the underlying process is a moving average process, when you look at the ACF and the PACF, it's exactly reverse as if you were looking at the ACF and the PACF for the autoregressive process. So the PACF will be tailing off for moving average model, but the ACF will just cut off, like really drastically. Okay. A good model candidate model would be if both the ACF and PACF are tailing off. Okay, so this gives you the indication of using both ACF and the PACF to identify. Now you may ask, why is that? Where did you come? Where is this table coming from? So one thing we didn't go over, and I really encourage you to after the tutorial to read some of the reference material, is to look at, for each of these models, there is actually a theoretical autocorrelation functions. There's a theoretical partial autocorrelation functions. From those functions, that this is the behavior of the ACF and the PACF. Now again, when you analyze data in real world, I don't know whether or not the underlying process is AR or MA or ARMA. So being able to understand the theoretical structure of the underlying correlation function is going to be very helpful for you to select a candidate or at least a set of candidate models. Okay? So I hope I answered the questions for trying to detect that, and we'll go for some of the details. So I'm continuing to use the same series. First thing we're going to do is that, again, I just pick a number. I just leave out a few observations. So this series have 120 observations. I keep 95% of those for the training. the training model, and then I leave out a field for the forecast, for the testing set. Now, one big difference here is in many other data science exercise, when you choose your training set and your testing set, you may randomly select observations for your training set. For time series, you cannot do that, right? Because if you do that, you break the dependency structure of your underlying data, right? So you cannot just say, okay, I want to randomly select 80% of the observations, and then let me estimate a model, okay? So this is the biggest thing. So that's why I only leave out the last part of the series for us to do the forecast. Of course, it depends on of the purpose of building the model as well. If your purpose is really to understand the past behavior, maybe in some cases the random selections may make sense. Okay. So we repeat what you just did. So we look at the series. We try to. Oh, I actually shouldn't run it, but I ran it. Okay. So for this particular series, looking at the data here, I hope that you actually record some of the observations you have about this series, right? So it doesn't have a very strong apparent trend over this period, this time period from roughly 2006 to 2016 or end of 2015. But it has quite a bit of fluctuations. It's not seasonality, but it has a cycle. It also slowly tailing off, and for the MA model, it cut off pretty drastically after two ACL, after two partial autocorrelations. So it looks like, and I haven't differenced anything. So this is the raw series already. So it looks like a good starting point is an AR2 model. Again, because this is a whole class of functions in Python, so it's the whole class of ARIMA functions, ARIMA models, I should say. And so, at least for the rest of the tutorial, I will keep saying, for example, even the AR2 model, I'll actually speak ARIMA 200. So 0 here represent the 0 times in terms of the differences, and then 0 in terms of the moving average components, okay? So if you write it down as a model, write it down as an equation, it will be yt equal to c1 yt minus 1 plus c2 minus 2 plus the epsilon t. So always keep in mind what is the underlying model you're estimating. Okay, so I'm here. So go ahead and estimate a model. And so to estimate this, model, these are the functions we use. The whole class of functions in the stat model is actually pretty straightforward in terms of the fit and then summary after you fit the model. So you see this structure again and again. And again, I'm using a SARIMAX class of functions, even though I'm not specifying any seasonal components. I only specify the non-seasonal component of the model. And so after you estimate a model, you actually can summarize it, the result. So what are we looking at here? So we are looking at, okay, first of all, the number of observations being used to estimate a model or train the model. The model in particular, so again, we specify AR2 model. So these are the coefficients associated with that, the standard deviation, the C statistics, and whether or not these parameters are significant. In this case, it is. It also gives you statistics to look at AIC and BIC Akaike information criteria and Bayesian information criteria. These are the measure of the in-sample fit of the model. Not out of sample, it's in-sample fit of the model, meaning after I estimate a model, whether or not the model that I propose is a good fit of the data that I used to train the model. Both AIC and AIC and BIC are functions of the estimations of the underlying the standard error of the residual, and so which is a function of the the log likelihood of that, and both AIC and BIC is that plus some penalty terms. As you know from linear regressions, you don't want to put in too many terms, and so this help you to penalize if you put in too many parameters. In forecasting, it's particularly important that you keep in mind the parsimony as the principle, so don't put in too many parameters, because there's a consequence if you put in a lot of the parameters into the model. Because at the end of the day, if you do want to do forecasting, so let's say I want to forecast for the next 5 period, if you have many lags, well, which means that for each of the forecasts that you have in the future, you have to use that many informations in the past for you to produce the forecast. So keep that in mind. The following statistics here, remember after we estimate a model, we actually have to look at whether or not the model satisfies the underlying assumptions. One of the key assumptions of the model is that if the model is specified correctly, the error term is supposed to follow a white noise process. I actually, by the way, in this tutorial, I haven't defined what a white noise is. So a white noise is a normal random variable. It's a series of normal random variable that are independently and identically distributed. So it's IID normal random variable. So if my model is specified correctly, the underlying residuals that you look at should look something like a white noise, approximately at least. Okay, so keep that in mind. And these are the statistics associated with to test whether or not the underlying distribution is normal, whether or not the underlying distribution has correlation, etc. We'll talk more about that in maybe about 5 minutes. So just keep that in mind. So the output result here is pretty rich. A little bit of a digressions. So my colleague here also wrote down some functions for us to test a series of models simultaneously. So remember I started a candidate model, ARIMA 200. But hey, maybe you want to estimate a series of models. Maybe I want to try 201. I want to try 202. I want to try 300 as well. Right, so we actually, so Mac actually wrote functions here to allow you to test all the way up to a ARMA model of order 4 in both autoregressive component and moving average component. Okay, you can play around with the functions later. So this is a little bit of a digression, and hopefully, if I can get to section 5, Matt will tell you more about it. If not, you can go play around with it as well. And in fact, if we do that, here actually summarize how many? 20. It summarized 20 models here in terms of the BIC. Because in fact, for those of you who use R, for example, I have an octo ARIMA functions to allow you to choose the quote-unquote best model. Now, be very careful whenever some software tell you to choose a model automatically. There's no such things as automatic in the sense of it has to be, the choice has to be a function of some underlying metrics. In this case, it could be the lowest AIC. It could be the lowest corrected AIC, or it could be the lowest BIC. So these functions is to illustrate that we could replicate that. We could replicate that kind of mindset, and we choose the model, or at least we output which model gives you the lowest BIC. So in this case, the model that gives lowest BIC seems to be ARMA 11 model. Okay, even though I try AR2, even though I try AR2, the lowest the model that gives you the best according to BIC is actually ARMA11. Okay, so again, this function is for you to experiment a little bit. Now, remember, this is just in-sample fit though. At the end of the day, you may care more about forecasting, which is the out-of-sample performance of your model. We'll get to that in a little bit. So just keep that in mind whenever you use a function that called octo whatever, which I always tell my colleague, be careful what is the octo based on. Okay, I actually spoke a little bit about the model diagnostic. So in Python, after you estimate a model, you also can, this function is very nice. It allows you to plot the diagnostic graphs, meaning it plot whether or not the underlying residuals, standardized residual in this case, look more or less like a white noise. And so, by the way, let's go back to why we want to simulate the underlying process. So I haven't done it, but maybe after the tutorial, you can go back to use the tool to simulate what a white noise look like. Compare that series and see whether or not that series look like this series, right? Just visualize, right? When you look at a graph, you can already tell, oh, wow, okay, that graph look more or less like a white noise, okay? The distribution is fairly normal. In fact, you can look at it based on the QQ plot. At the end, there's a tail that is flatter than a normal. But based on the statistics that we actually show above, it cannot reject the hypothesis that this is not a normal distribution. And this is the correlation of the series. It's not correlated. So at least this particular model looks reasonable, okay, after you do the diagnostic. We include some of the references here for the formal testing. So each one of, now, this diagnostic is just visuals. Remember, in the back, there are also formal statistical testing that you should test whether or not, the underlying assumptions, meaning, this is a non-constant variance, non-normality, and serial correlations. These are things that are tested under this, okay? In this notebook, we also include some functions to actually replicate what we have, what is included here as well, these statistics. So you can also try that. Okay, so model performance in terms of in-sample fit. In time series, it's nothing better than looking at it visually. So after you estimate a model, after you check that the model at least is reasonable, then you should look at the performance of the model. Honestly, if the model it doesn't even satisfy the underlying assumptions, you should really go back, re-specify your model before you look at the performances. Otherwise, you are telling people about the performance of a model that is not valid. Okay, so let's check this out. So the in-sample fit looks pretty good, which is right the red line and the blue line. Based on the model that I use. Again, I only use the model that is AR2 model or the ARIMAS 200 model. I didn't use the model that is based on the best BIC, at least in this example. And then on top of that, we left out some sample. We try to forecast what the holdout observations. Now, I actually will have you do some exercise, and then I will come back to ask you this. So I would like you to just follow this procedure, but I want to talk a little bit about why the in-sample fit looks so good, but my out-of-sample forecast doesn't look that good. This has a lot to do with the structure of the model. But I'm not going to talk about it right now. I'm going to talk about it in maybe 5 minutes. Okay, lastly, before we go into some of the exercise that I want you to try the procedure, at least I want you to get the working knowledge of this model building procedure. the AIC, remember the AIC and BIC talks about the in-sample fit. When you do out-of-sample forecasting, there are also metrics that measure the out-of-sample forecast. Here we include 3 of those and the references of those. One of the ones that I use a lot is the root mean square error. So meaning you take the residuals, you take the differences of the residual, you square it, you sum all of the differences, at least in your out-of-sample forecast. But because you square them, right? So the unit is all square. So you have to take square root to get it back to the original unit, so that number actually make a little bit of sense. There are others, right? You can take the absolute mean, absolute error, and then absolute percentage error, etc. They are all in the same principle, right? Meaning there are some functions of the errors. Okay. Let's move on to do exercise 3, and follow the procedure I lay out above, and I lay out already all the steps already. So just run the code. Okay, take 5 minutes to do it. So why don't I? Because I only have 30 minutes left. I really want to go over the seasonal ARIMA model, at least to give you some working knowledge to start after the tutorial. And then I want to spend at least a few minutes at the end to go over some of the practical suggestions and references I have. And Matt will also talk to you a little bit about it as well. So maybe let's spend the next 15 minutes or so on the seasonal model. Okay, by the way, for the exercise, I try using an AR2 model. I import the series, I plot it. Again, it doesn't look like there are any trend at all. And the octocorrelation function and the partial octocorrelation functions. AR2 seems to be a good start. You can try AR1, but I try AR2. And I go ahead and estimate a model. And it looks okay. It doesn't mean that I can just stop here, right? Again, at the end, it will still depend on what are you looking for when you build a model. Do I just want to fit the time series, or do I really want to use the model to forecast some of the near future? Yes?
What about the log part? So that there was a section in 2B where it says...
2B, 2B, yes.
Sorry, 2C.
2Cs. Yes, that's a good point. So sometimes the raw series itself may have very strong trend, may even have seasonality, which I'm going to show you as well. So it requires some transformations before you even attempt the ARIMA model. And so the transformation could be, you may have to different it one time. Now, this function actually differentiates it for you, so that's good. But it could be that, remember that one of the series I showed you earlier is fluctuate, it has trend, and then it explode, or not explode, but the variation get bigger and bigger over time. So in some of those cases, you may want to take the log transformation to stabilize the variance before you even try the differences. So here, what I really, this series that I gave you, it doesn't run any transformation, but in practice, transformation are actually very common. So log is being one of those, difference is being another one. So thanks for the questions. So that's why I didn't do anything here. Yeah, because I simulated series, that's why I know. Okay, so the model that I use, again, even though it looks reasonable, the fit is not very good, right? So what it really means is that I may have to go back and retry some neighboring model and try other orders, okay? Before I move on, I want to ask you one question. Remember before this looks really good in terms of the in-sample fit. It's an AR2 model, by the way. So I used the last 2 legs. but my out of sample fit is horrible. Why is that? Actually, by the way, it's not the entire out of sample fit. It's really after maybe 2 period in the future, 3 period, 4 period, and 5 period. I only did 5 step ahead forecast. It's only after the second step that my forecast started to deteriorate. Why is that? Any thought about that? Yes? I'm overfitting, okay.
So the 2 steps that you generated are wrong and it's cascade.
Mm-hmm. Any other idea? So then actually, in many of the other techniques that we use in data science, that could be an indication. It turns out that in the case of time series analysis, especially in the case of the class of autoregressive integrated moving average model, remember that whenever we talk about forecasting, we need to know what information do I have as of a particular point in time to allow me to forecast the future. In this case, my model is trying to capture or use only the information in the past 2 periods for me to forecast the future. Now, if I do a 5-step ahead forecast, 2 periods later, I do not have the real information anymore. I am forecasting the future based on my forecast of the near future, right? And so it's not that my model is bad. It's just that I don't have the information allow me to do the forecast. Now, that is a very, very important considerations when you do forecasting. What information do I have to allow me to do the forecast when you build a model? And this is one of the most prominent example of, wait, why your in-sample fit is so good, why don't you forecast for the next 10 years? Well, tell me about the information for the next 9 years. I will tell you what it's going to look like for the next 10 years. Right, so this is the case. Now, so that's also allow me to talk a little bit about why don't you use explanatory variable? So in fact, this class of functions allow you to input an extra variables for you to do the forecast as well. So if I want to forecast the sales, maybe I want to forecast whether or not the company give any discount over time, right? Don't you think that would be helpful? I think that would be helpful. However, if I want to talk about forecasting in the future, which means that, let's say if I want to do 3-step ahead forecast, you will have to tell me what are the discounts that I need in the future so that I can tell you the sales 3-step ahead, as an example. So anytime you import explanatory variable in your forecasting model, depending on the index, depending on how many lags you are using, in the forecast you may have to forecast the explanatory variable before you can forecast the variable of interest. Okay? Just keep that in mind. So sometimes when people ask me to build model, they ask me, oh, why don't you use this set of variables? And my answer to them is, yes, give me the forecast of those variables first, then I will build my models using those informations that you give me. Now, it's not to say that not to put in any explanatory variable into your model. In fact, have you guys heard of stress testing by the Federal Reserve? The Federal Reserve stress test the top 19 banks in the country. Have you heard about that? No? Okay. Have you guys heard of something called scenario analysis? So let's say I build a model, not only do I have yt equal to some function of yt minus 1 and yt minus 2, maybe I have xt minus 1 and xt minus 2 as well. X is some other variable. So you can utilize that and say, well, if the future of the x's look like the following, then I can use that information to tell you what yt is. So in stress testing, for example, which is our government do a lot on the top financial institutions, what they're doing is that they tell you if the economy are going to go in certain ways, and I'm going to tell you how it is going to look. Let's say the unemployment rate go back up to 10%. Then you have to tell me how your, let's say, earnings going to perform, or how the value of your portfolio is going to look like. So in that case, you will have to build your model using those extra informations. In this case, unemployment rate in your model. Okay. Okay. So now let me move on to the seasonality. I only have 20 minutes left. Okay, so that's notebook number 4, section 4, called SARIMA. S stands for seasonal component. At the beginning, we introduced a series that have seasonal component in it. So again, I import the series. As you can see, some of these steps become repetitive, right? Once you understand the most simple set of models, you can actually generalize it pretty easily. The only exceptions with the seasonal component, the ARIMA model with seasonal component, is that the notation is very dense. So at least I want to get through those. So this is the airline passenger series that I showed you before. Look at the ACF and PACF. So not only there are very strong correlations, but then you also see that there is spike maybe every other year. Now only plot 20 lags. I can include up to 40 lags, for example. I can do like 40. Whoa. Oh, okay. Of course, I have to run the notebook above before I do that. Okay, it doesn't work. So anyway, so I need to run those all the way down here. But you can include up to, let's say, 40 lags and see that the pattern of the time series right here. Okay. And so in this case, I do have a pretty strong trend. And so that's back to the transformation. So one way I could do is to differentiate one time to take out my trend. So first differences is a very common way for people to take out the trend. You can estimate the trend and take it out too, which is, I think, what he asked me at the beginning. I can estimate a linear trend and I can take that out. But in this case, I can do a difference and then take out the trend. I can also take log. I messed up my graph, but I can take log first. The trend is still here, but I totally stabilize the variance. You see, compared to this graph, till I say stabilize the variance. On top of that, I can take the first difference of the lag. So taking difference on log is very similar to doing a percentage transformations. When the difference is small enough, they're almost identical. So yt minus 1 divided by yt minus 1 is close to log of 1 plus the return. So this, you see that very clearly, the seasonality here, the correlation that is based on a year ago, 2 years ago, 3 years ago. You see that? So this gives you the indication of choosing the order for the seasonal components. So we have already done that for the non-seasonal component. Right now it's the same thing, but for the seasonal component, except the notation is just so much more complex. So that's why I want to introduce this to you first, to look at the graph before I even introduce the math. So this graph you see before you see the strong seasonality around the summertime. So seasonal component. So if I have a purely seasonal ARIMA model, it looks almost identical to the ARIMA model, with the exceptions that the backshift operator right now is a multiplicative of order S. So S in this case, it could be 12. If it is 12, then my model, so current informations, is a function of the information 12 months ago, in this case, or 12 periods ago, as well as the shock and the shock 12 periods ago. So this one is at notation. I should have written as, oops. So I should, where is it? Right here. So I should have, because I don't have any non-seasonal components, so those are 0, 0, 0. And then this one corresponding to the autoregressive component associated with the seasonal component. And then this another one is the moving average component associated with the seasonal component. 12 here is the period in your seasonality. In this case, it's 12. Again, if you look at the documentations from stat models directly, it's a lot more dense than this. That's why I want to create an example for you to unpack some of these notations. This is very similar to what we talked about for the non-seasonal component ARIMA model, except this applies to the seasonal components. So the general form of the multiplicative seasonal autoregressive integrated moving average model actually looks something like that. Okay, and so that's why when you implement the model, you have to specify all of these orders for the non-seasonal component and the seasonal components. Okay, this is one more example. I'm not going to go over them. Once you have that, the steps of building the models is roughly identical. You just have to identify what is the seasonal components as well as the non-seasonal component using the ACF and the PACF. Then you can estimate a model, you can look at the residual, do the diagnostic, do your forecasting. So again, I estimate a model, I look at the residual, and then I give you an exercise. So that's pretty much it for the seasonal component autoregressive moving average model. I want to spend a little bit of time to maybe 5 minutes, Matt. In notebook number 5, Matt actually written a lot of the functions to allow you for what we call selecting a model heuristically. So in practice, you don't just select a model based on AIC. Again, whenever you select a model based on some metrics, you have to understand what that matrix really is measuring. And so there are several considerations. I want him to at least give a few minutes of talking about a heuristic, and then I will close it up to give you some references.
All right, hey guys, so in the section 5 notebook, I have outlined at the top just kind of some of the methodology. It incorporates some of what Jeffrey talked about for the Box-Jenkins approach, but it incorporates some additional methodology that I've used on some of our forecasting projects, where we look at not just, how do we choose the AR or MA orders from the autocorrelation and partial autocorrelation plots, but also how do we interpret the output from the fit of those models. So stats models will automatically run a number of statistical tests, mostly on the residuals. There's a table that shows up below your order coefficients, which you've probably seen. I don't know if one's plotted in here, I forget, but so the idea is to use those statistical test results to also help you choose a model. So I've kind of just talked about my approach, kind of an approach that I've developed working on these projects with Jeffrey and some of our other data scientists. So not only, do we want to plot the data, as I've kind of discussed, written here, and then choosing our appropriate model form. Are we going to have seasonal data? Are we going to have external variables? That's the X, which we didn't really get to today. And then check for stationarity. There's a number of tests to do that. But we can also then, choose the best model based on some criterion. We can look at the statistical test, as I mentioned, or we can also look at out-of-sample forecast error. That might really be what you want to get at for when you're making these ARIMA models. You want to make some prediction about the future, and you might want to choose the best model, the model that performs best on some holdout period, so you can use that model in the future to make a forecast, which I just recently did for one of our clients. So I have a number of functions here. They're kind of cited. I've used some functions that we found on interesting blog posts about time series analyses, but we've modified these a bit, kind of for our own purpose. So there's one about testing stationarity. Here's our autocorrelation and PACF plot. There's this is kind of rerunning some of the stats models statistical tests about heteroscedasticity and normality of the residuals, things like that, as well as some additional tests looking at, another measure of serial correlation. We didn't get too much into this, but the roots of our characteristic ARIMA equation need to be outside of the unit circle. That tells us about stationarity and invertibility. And I've written kind of a more extensive function here for doing a model grid search, which you saw a basic version of earlier with that 5x5 heat map. So I've loaded up a data set here and run this grid search on the data set using just a small number of parameters. This is liquor sales in millions of dollars between about a 10-year period here. I think this data set was loaded up in a previous notebook. But if we kind of look at, whether this series is stationary, and we could see it just by looking at it here. This is definitely not a stationary series, and the test here, the augmented Dickey-Fuller test, tells us so. The p-value is clearly not below 0.05. But if we take the first difference, then we might say that this series is stationary, so that kind of informs us about the D parameter for the set of PDQ model orders that we would use. Jeffrey also mentioned doing a log transform, which by itself doesn't make it stationary, but if you take the first difference of that, it's also stationary. So whether you want to do that or not is up to you, and there's no right answer, but you can see how the model performs. So doing a big grid search, here it's just going over some ARIMA parameters as well as seasonal parameters. When it runs through that, we can kind of get out, a set of model results. We have things like AIC and BIC, but also whether we violated assumptions of normality, whether there was serial correlation. The Durbin-Watson statistic also tells about serial correlation. So you might use the results here. The Durbin-Watson statistic tells about the serial correlation of, I think it's the AR1. So use like an autoregressive 1, so just one step back, but this is a test on the standardized residuals. So after you've fit a model, subtract the model from the actual data, and then a test on those residuals to see if they're serially correlated. But anyway, so you can use the results here to kind of help you make an informed decision about what model might be best to choose. So you could choose just based on the lowest BIC, but we can see that there seems to be some serial correlation in the data here. So we might want to actually reject that model and choose one that doesn't violate that so much. So we might make it all the way down here, where the parameters would be 212, 012. So that means, the PDQ of the ARIMA part is 212, and then of the seasonal part is 012. So we do one seasonal difference with a seasonal number of 12. This is monthly data, so that tells us that 12 months back there was correlation there in the data. So these are just some pointers for how you might proceed in model selection. I think choosing just based on AIC or BIC is not necessarily the right answer. One more time? Yeah, that's right. Yeah. This is less about choosing features. So the question was, would we use the results here in some additional models, such as linear regression, to know which model to choose? I would say at this point, it's more kind of it's more a choice of the person who's doing the analysis and less the choice of some kind of additional model fit. Because there's not necessarily one right answer for the time series that you're analyzing. Does that make sense? Yeah. Well, there's many different ways to measure which one performed the best. It might be based on, average forecast error for some holdout period of data. You might choose the best one based on BIC, but unfortunately, there's not one right answer. And so at this point, it's that's why these are heuristics and not set rules, why we can't just have some automated model selection. So at this point, it's up to you. Choose your own adventure. There's a lot of resources here that I've listed, many of which we used in the construction of these 5 notebooks, kind of for using some of their functions and modifying them, or for inspiration about data sets. So hopefully you'll find these to be good resources in your own time series analyses. All right, thanks. I'm going to give the mic back to Jeffrey.
So to your questions about choosing models. Whenever someone chooses model based on any metrics, you like I said, you really need to know what the metrics is really measuring. I think almost all of the textbooks that you read will talk about choosing a model based on in-sample fit. So meaning here is measured by the Akaike information criteria or the Bayesian information criteria. However, in practice, we have found that not necessarily that you just want to use in-sample fit, right? Because some may want to know, okay, I build a model, I really want to know my forecast. So in that case, a good measure would be the forecast performance, not necessarily how well I did to explain the past. So that's why that tables here that lists the top 10 models. So actually, the research that Matt did has about close to 200 models. I think it's 180 something models. It only lists the top 10 model by the BIC. Right? You can actually modify the code here and list the top 10 model by out of sample performance. Yeah. So you can sort it by, let's say, the root mean square error too. Then it will show you a different. So these are the model numbers. The first column, model number 16, model number 33 by lowest BIC. Okay, you see it here. You can sort it by lowest AIC too. But again, it's just a way for people to do it. Again, it all depends on the problem that you are trying to solve. One last thing. So the resources here, so these 2 are free textbook. That's why we list it for you guys to check out. This textbook is pretty good. In fact, this textbook is by Rob Heyman. He is the guy who actually wrote the forecast package, which is extremely popular for R. And then this one is by these 2 professors. They have a more comprehensive and difficult versions of the textbook, but they put in an easy versions as a PDF format on their website for people to download. So, hope you can start your adventure in time series analysis.